Okay, so now let's look this example of lifting a load. So this is a hydraulic system. In this hydraulic system, we have a tank here. The tank is providing the hydraulic fuel or the hydraulic fluid. The hydraulic fluid is now taken by the pump. The pump is going to produce the high pressure. So the high pressure fluid is in red color. Now this high pressure fluid uh, can pass through the pressure relief valve. If the pressure is higher than required, then some of the fluid is going to be relieved of the pressure and return back into the tank. Otherwise, the high pressure fluid is going to go into the DCV. Now, this is a 4-port. We have a port P, we have a port P, we have a port A, we have a port B. We have a 4-port and 3 positions of the spool. We have a 4-port, 3-position, 4x3 DCV valve, and the position shown here is such that port P will be connected by port B, which is going to go into the actuator such that it's going to retract the cylinder, and then while retracting the cylinder, the fluid, the low pressure fluid is going to return from port A to port P, and then it's going to go back into the tank. So this is the example. If suppose, let's say if the side of the piston is connected with the load, so by retracting the cylinder, we are actually lifting the load. So this is the example for lifting the load. Now let's see the other example. Suppose when we want to lower the load. So if you want to lower the load, then instead of connecting port P to B, we will connect the port P to A. The spool position would be such that the P will be connected to A. So the high pressure fluid is now going to go into the cylinder such that it will extend the cylinder, and the low pressure fluid is going to return back from port P to T and then go back into the tank. But in this case, because of the cylinder extending, the piston is going down, so the load will be lowered. We can have a third position in such a way that all the inlets and outlets are closed. So in this case, the high pressure fluid can neither go to A nor go to port B because it is completely stopped by the spool. So whatever the fluid, high pressure fluid is produced and then flown, is going to return back through the pressure relief valve back into the tank. So in this case, the fluid inside the cylinder, whether it is on one side of the piston or the other side of the piston, and neither of it can leave the cylinder nor can enter into the cylinder. Since there is no way leaving or entering the cylinder, so the cylinder is going to stay there, piston is going to stay there at the same position, so the load is going to stay there at the same position. So this is basically 3 different positions of the spool. These 3 positions are also shown here. This is for the case when the load is lifted. This is for the case when the load is lowered, and this is for the case when the load stays at the same position. So 3 different positions of the spool uh, shows the functioning of the DCV. Okay, so this is basically a 4x3 DCV. So control valves are used to control conditions such as flow, pressure, and direction of flow. Pressure control valves could be there, flow control valves could be there, direction control valves are check valves and direction valves. Let's discuss about the pressure control valves. So pressure control valves are such that they are connected within the piping system at points where we feel that the high pressure would be generated, okay, and where we want to relieve the piping system from the high pressure. So it is composed of a seating arrangement and a spring connected with a screw. So the screw is going to adjust the compression of the spring and actually the amount of pressure of the fluid correspondingly. So when the pressure of the fluid is such that it is good enough to push the seat away by further compressing the spring, okay, is going to open the port here, okay, and the excess fluid is going to go out of this port, and so the pressure will be relieved in the piping system. So a pressure control valve is used to reduce the amount of pressure in a tank or system of pipes. Okay, it is how? By this seating. Okay, so this seating is actually keeping the pressure control valve closed. PCV is closed. But once the pressure in the piping system increases higher than the desired amount, so this pressure in the pipe is going to push the seat in this direction such that the port is open and PCV is open, and actually the pressure can be relieved. So this way we can actually protect the piping system by actually relieving some of the pressure from the piping system if the pressure goes above the required limit. So this is the functioning of a pressure control valve, normally referred to as PCVs. Then we have FCVs, which is the flow control valve. Flow control valve is very similar to the valves we have in our homes, in the kitchens or washrooms, wherever we have the wash basin. So we have a tap, and if you see there is basically a screw valve, and through the screw valve we can open the we can open the water tap, we can close the water tap, we can fully open it for the large amount of flow to flow. We can just adjust it so that a specific amount of flow can come out of the tap. Okay, so this is basically a flow control valve. This is the screw. This is the screw tapping, which can be lowered by rotating counterclockwise or clockwise, and which can be moved up and down. And with this, the opening is also changed, and so the opening is also maneuvered so that the amount of flow going out of this control valve depends upon how much is required based upon the position of the seating. Then we have the check valves. The check valves are such that in case of the check valve, we have a valve clapper here. This is basically a valve clapper. Okay, so like for example, in this case, the fluid is supposed to flow in this direction. So when the fluid is going to flow in this direction, so what will happen is that it's going to push the clapper up, and the fluid can easily flow in this direction. However, if somehow the fluid direction is changed, is reversed, and the oil start flowing in the opposite direction, it will push the clapper down, and the clapper is actually going to block the path of the fluid motion. So the fluid motion is allowed only in one direction, and in the other direction, the fluid motion is actually stopped. So with the help of this valve clapper, the check valve allows the fluid motion in one specific direction. And this is actually a directional flow control valve. There we can have direction valves shown here. This is a spool DCV. This is a 4x3 direction control valve, since there are 3 different positions of the spool and 4 ports, P, T, A, and B. So this is a 4x3 direction control valve. This is a spool valve. Mostly spool valves are used. In hydraulics, the pressure port is designated P, and the return port is designated as R or T for tank. The other ports are designated as A and B, boxes to identify normal and operating positions. So whatever the states are there, we for each and every position, we have a separate box. Arrows to identify the flow direction. In pneumatics, the pressure port is numbered 1 and the exhaust port is number 3. The other 2 are number 2 and 4. So this is also one difference between the pneumatic and the hydraulic systems, how they are represented in the schematic diagrams. In case of the hydraulic systems, we do not represent them in terms of the numbers, but in case of the pneumatic systems, we represent them in terms of the numbers. So pressure port is always 1, and exhaust is always 3, and the other ports are 2 and 4. So this is, you can see here, This is a specific representation of this is a specific representation of a DCV. When it is operated by hydraulic, then it is P, T, A, and B. When pneumatic, then P is always the pressure port, 3 is the exhaust, and 2 and 4 are the ones which are basically connected to the cylinder. This is an example of 4-port, 3-position directional valve. There's a 4 ports, P, T, A, and B, and 3 different positions. One position shown here, the other position here, third position here. Okay. And since it is spring operated, so the spring is shown on one side, and on the other side we have a lever. So that's shown here. Then this is basically 5 ports, 3 position. So we have here 5 different ports. We have port A, port B, then we have port T, port P, port T. Okay, there's a 5-port, 3-position direction control valve. Next are the pneumatic circuits. In the pneumatic circuits, we have flow control valves the same way as we have one valve which is a shuttle valve. In shuttle valve, what happens is that we have 2 air inlets, P1 and P2, and 1 air outlet A. When compressed air enters through P1, the sphere will seal and block the other inlet P2. Air can then flow from P1 to A. When the contrary happens, the sphere will block inlet P1, allowing air to flow from P2 to A. So we have 2 inlets. Okay, so one is, you can say this is P1, other is P2, and A is the one which is going into the cylinder. So in case if the fluid is coming, pressurized fluid is coming from P2, so we have a ball here. The ball is going to block P1. Okay, and the fluid is going to directly go from P2 to A. Okay, and in case if the pressurized fluid is connected to P1, then it will push the ball on the other side, and the ball will come here and it will block P2, and then the fluid is going to enter from P1 to A. So in case of the shuttle valve, only one of the inlets is open at one time. Okay, and schematically, diagrammatically, it is represented as this. Okay, the position of the ball shows which side of the port is closed. So wherever the ball is, that side of the port is closed. The other side, the port is open. Okay, now let's discuss a little about circuit design problems. Here, this is one of the problem. We're not actually going to solve the problem here, but we are going to look at the possible solutions and the factors that needs to be considered while solving the problems. In a sheet metal forming press, the shape to be formed is hemispherical cup of radius 15 centimeter in 2 millimeter thick mild steel sheet. The force required to deform sheet is 8 kilonewton. The forming hammer should approach job from a distance of 30 centimeter. The production rate required is 240 components per hour. Calculate and suggest the following specifications of the various hydraulic components used. So we need to find out what is the hydraulic cylinder bore and diameter. Obviously, we are not actually designing the hydraulic system, so we have to design all the components of the hydraulic system. So the most important component of the hydraulic system is the hydraulic cylinder. So what is the bore of the cylinder? Bore of the cylinder means cylinder diameter, and that means the piston diameter. And what will be the length of the cylinder? So that will be the stroke length. Then about the pump pressure and the flow rate. So we need a pump, and what would be the pressure in the pump, and what would be the flow rate through the pump. Then obviously an electric motor will be connected to the pump to run the pump. So we need to know that what is the horsepower of the electric motor. Then we need to have a reservoir tank. Okay, both in the case of the hydraulic as well as the pneumatic system. So we need to know that what should be the size of the reservoir, and then obviously the size of the pump inlet and discharge tubings. So these are some of the things which are basically needed to actually perform the circuit design calculation. So there are several factors that needs to be considered. Let's say, for example, if we're talking about the cylinder selection reasoning. Okay, we can have a very large diameter cylinder, but large diameter cylinders will have will there can the advantage is that they can operate at comparatively low pressure, but then if we need them to operate at a larger speed, then we need bigger pump. The smaller diameter cylinder, on the other hand, can operate at will need to operate at a very high pressure, uh, but normally can require only smaller pump to provide the specific speed. So, anyways, this is always there's always a trade-off between uh, different things, different variables. We have to look into consideration that what are the acceptable ranges for our application. Then what capacity of the pump is needed? Okay, so the capacity of the pump should be that pump should be able to produce uh, the maximum cylinder speed required. So it should be based upon how much is the maximum speed of the piston needed inside the cylinder. So so that pump should be able to produce the pressure of the fluid such that we should be able to get the speed of the piston inside the cylinder with whatever is desired for our hydraulic system. Then in that case, the flow rate is basically the cylindrical area multiplied by the stroke divided by time. And based on that, the pump is going to be selected. Okay, what size of reservoir should be used? Normally, the pump capacity is represented in liter per minute. So based on whatever is the pump capacity, the reservoir should be able to uh, withstand the hydraulic system for at least uh, 2 to 3 minutes, even if when the pump is not working. So even when the pump is stopped working, the reservoir should be able to withstand for 2 to 3 minutes. So that means the reservoir capacity should be based upon the pump capacity. If the pump capacity is whatever the liters per minute multiplied by 2.5 to 3 should be the size of the reservoir in terms of the liters. Talking about the size of the pump inlet, for the inlet flow velocity, normally industrially is between 60 to 150 centimeter per second, depending upon the application. And then regarding the size of the discharge tubing, again, the outlet flow velocity should be between 200 to 450 centimeter per second. Relief valve selection depends upon the pressure ranges and the valve port size. The direction control valve should be based upon the function, that what kind of control valve is used, needs to be used. Regarding the hydraulic circuit, we have to do the following calculations. Okay, so we need to know that how much is the pressure needed in the system. So that depends upon our the fluid piping system. So pump is adding 5 horsepower to the fluid. Pump flow is this much. Pump has 0.0254 meter inside diameter. Specific gravity of the oil is needed. Kinematic viscosity of the oil is needed. Elevation difference is needed. Pipe length, whatever is there in the system that is needed. So this is all the type of calculations that you have gone through in fluid mechanics course throughout. So after doing the hydraulic circuit analysis, then we can go for the solution. First, we need to solve for whatever the velocity that is needed there inside the cylinder. Then we can go for the velocity head at station 2. We can talk about, we can find out the Reynolds number. Correspondingly, we can find out whether the flow is laminar or turbulent, find out the friction factor, determine the head losses due to the friction factors using the Darcy's equation, calculate equivalent length. We can use it in the Bernoulli's equation for pressure head calculation, and we can use the way we can calculate the pump head correspondingly to find out that what is the pumping pressure needed, what kind of pump is needed to run the system. Anyways, we were not practically solving the problem here, but to look at the design considerations which are there for uh, for actually solving the or problems related to hydraulic system design. Okay, let's discuss a little about the safety of operation. Okay, we always need to keep in consideration about the pressure and temperature ratings. Why do we need that consideration? There's always a ceiling between the piston and the cylinder. Okay, if the seal is broken, then the fluid can move either side of the piston, okay, and that would actually damage the piston cylinder device and damage the operation of the hydraulic system. So the sealing is basically there for a specific temperature and pressure rating. So if you use a wrong sealing at a different temperature pressure set ratings, then the sealing will fail and there will be leakages. Okay, then we need to have interlocks for sequential operations. Suppose if we have a system, hydraulic system, where after one operation, then the other needs to be initiated. That then once the other operation is completed, then the third needs to be initiated. So there needs to be interlock in the system that should ensure that the second operation will not start until and unless the first operation is completed. Then there needs to be emergency shutdown features. That in case of shutdown, okay, what needs to be done, what should be the default position of the valves so that the shutdown will not damage anything within the system. We need to have the power failure locks. In case the power failure occurs, then how the system is going to respond. The operation speed needs to be considered. Environmental conditions also need to be considered for the operation. These are the safety of operations which are needed in the design considerations. Then we need to meet the functional requirements, like for example, the performance specification, life expectancy of each component in the system. So overall, the hydraulic system should be able to have the life expectancy same as that of the machine to which it is applied. Then it should be able to facilitate good maintenance practice. It should be compatible with the electrical and mechanical components. It should be able to withstand operational hazards. So these are some of the functional requirements within that needs to be considered in the design. So this is about the first lecture for the case of hydraulic pneumatic systems. We discuss in generally about the hydraulic pneumatic systems, the components, their operation, okay, and regarding the designing of these systems, what kind of calculations are made. But in reality, we did not actually solve any problems, numerical problem related to it. So that's the end of today's lecture. In the next lecture, what we are going to do is we are going to discuss and we're going to cover some of the numerical problems for designing of these hydraulic pneumatic systems. If anybody have any question, you are more than welcome to ask. Otherwise, this lecture is over and you can leave now. Thank you.